So this is the seventh question related to application of Norton's theorem to electrical circuits. So we have taken the same circuit which we did in question number 6, but here we have to find the Norton equivalent circuit across these two terminals C and D. In question number 6 we did it across these two terminals A and B. Here we will do it across the terminals C and D. So first we have to determine the Norton current by short circuiting these two terminals. So let us redraw the circuit according to that. So 120 volt, 6 ohm, 3 ohm, 4 ohm, 6 ampere, then we have this 2 ohm and the short circuited terminals C and D. So now here, because of this short circuited terminal, this 2 ohm resistor will be not part of this circuit because the equivalent resistance will be 0 if we calculate the equivalent resistance across this area because of this short circuited path. So this goes out of the question. So now we have to find this current IN, Norton current flowing through this short circuited path. So we will be using let's say we will use mesh analysis here. So first let us assign the mesh currents. Here it is I1, let's say. Here let's say it is I2, and this is IN, Norton current. Now pay attention to another important thing. Mesh 2 and mesh 3, let's say mesh this in which the Norton current is flowing, let's say mesh 3. These two mesh have this current source, independent current source 6 ampere in between them. So when we will apply KVL, we will apply KVL to this two meshes combined together. It is a super mesh. Okay, two meshes having a current source in between becomes a super mesh. So another important thing, the auxiliary equation, which is IN minus I2 is equal to 6. If we apply here, IN is flowing upwards, I2 is flowing downwards. As 6 ampere is going upwards, so IN is predominant. IN minus I2 is equal to 6 ampere. This is the important equation. Okay, so now let us apply KVL to this first mesh, which is 120 minus 6I1 minus 3 into I1, considering I1 as the reference, I1 minus I2. I1 is flowing downwards, I2 is moving upwards, opposite direction as we are applying KVL to mesh 1. So mesh I1 is the reference. I1 minus I2 is equal to 0, or that implies 120 minus 6I1 minus 3I1 plus 3I2 is equal to 0. That implies 120 minus 9I1 plus 3I2 is equal to 0. This is the second important question here. So if you have any doubt, please watch the videos related to mesh analysis, super mesh, mesh analysis, nodal analysis, those videos. There I have discussed the basic concepts related to how to apply mesh analysis, nodal analysis, KVL, KCL. So please watch those videos. So this is the second equation for this mesh number 1. So now we will apply KVL to mesh number 2 and 3 combined, the super mesh. Okay, so here it will be, okay, minus 3, here I2 is the reference, okay, minus 3 into I2 minus I1, because they're in opposite direction, I2 minus I1 minus 4I2 equals to 0, because there is nothing here. Here there is no resistor in this mesh. Okay, like this, we'll apply KVL like this. Okay, that implies 3I1 minus 7I2 is equal to 0. This is the third equation. Okay, so now let us write equations 2 and 3. So here let us write equation 2, minus 9I1, okay, let us use a different ink, minus 9I1 plus 3I2 is equal to minus 120, and here it is 3I1 plus minus 7I2 is equal to 0. Let us say we multiply 3 here to this equation and then we add it, so it becomes 9I1 minus 21I2 is equal to 0. Okay, so minus 9 plus 9, it gets cancelled, plus 3 minus 21, it is minus 18I2. Minus 18I2 is equal to minus 120 plus 0 is minus 120. So you get the point. We wrote equations 2 and 3. We multiplied equation 3 with 3. So we got 9I1. Then when we added it, my I1, the variable, I1 variable got cancelled, and we got the equation in terms of I2. Okay, we simply used variable cancellation method. So minus 18 I2 is equal to minus 120. So I2 is equal to 120 by 18, which is simply equal to, let's say, 6, 12, 20 by 3 ampere. Now I2 is 20 by 3 ampere. Here we will use this auxiliary equation which we first wrote. In is minus I2 is equal to 6 ampere. So In is equal to 6 plus I2, which is 6 plus 20 by 3, which is equal to 38 by 3. 38 by 3 ampere. So it is coming around, let's calculate, 12.667 ampere or 12.67 ampere, we can also write. So In is coming 12.667 ampere. So that is the value of In. So we calculated In. So here simply we use the concept of super mesh to find the Norton current, because with these two meshes have this current source in between. So we simply used mesh analysis and the concept of super mesh to determine In. So we have got In. Now we have to find the Norton equivalent resistance. So we have calculated the Norton current, which we got is 12.67 ampere. So now we'll determine the Norton equivalent resistance across these two terminals. So for that we have to deactivate the independent sources. So here the voltage source 120 volt will be short circuited, and the current source will be open circuited. This is open circuited, and this is 2 ohm. 2 ohm, 4 ohm, 3 ohm, 6 ohm. Open circuited, this voltage source short circuited. So here the Norton equivalent circuit, Norton equivalent resistance, see 6 ohm and 3 ohm resistors, they are in parallel with respect to each other. The resultant is in series with 4 ohm, so plus 4, and that resultant is in parallel with the 2 ohm resistor. Okay, so it will be simply, this is 6 into 3 by 9, which is 18 by 9, which is 2 plus 4, which is equal to 6. 2 plus 4 is equal to 6. So we have 6 parallel 2, which is equal to 12 by 8 ohm. So 12 by 8 is coming around 1.5 ohm. So 1.5 ohm is the answer. So 6 parallel 3 plus 4 parallel 2. 6 parallel 3 we got 2, 2 plus 4 is 6, then 6 parallel 2 is 6 into 2 12 by 6 plus 2 8, which is 12 by 8, which is 1.5 ohm. Okay, so the Norton equivalent resistance is Rn is equal to 1.5 ohm. So In is 12.67 ampere and Rn is equal to 1.5 ohm. So Norton equivalent circuit will be something like this. .67 ampere and 1.5 ohm. Okay, so this is the 7th question related to application of Norton's theorem to electrical circuits. Okay.